Hello, I am Vedant and I will be introducing the project. Our group members are Kshitij Badarpurkar, Aditya Saran, Swaprabha De, Akshay Chaturvedi and Vedant Chaudhary. Our project topic is practical continuous variable quantum secret sharing using local oscillator. Secret sharing, which was originally proposed in the late 1980s, aims to deliver multiple secret keys to a group of remote users. In a typical kn threshold SS scheme, the secret is divided into n shares and it can only be reconstructed from at least k of these shares. Due to rapid progress in quantum technologies, a quantum version of secret sharing was proposed, which guarantees security based on laws of quantum mechanics rather than computing complexity which is used in the classical case. Further, QSS can be divided into two parts: discrete variable QSS and continuous variable QSS. Discrete variable QSS uses the polarization states of a photon to transmit the information of key bits, while continuous variable QSS encodes key bits in the quadratures of the optical field. General CVQSS schemes were based on entanglement source, which is currently difficult to prepare. But a solution has been proposed that we can solve this problem by using weak coherent source. So in order to develop that, a CVQSS scheme using discretely modulated coherent states was proposed. Recently, CVQSS using multiring modulation is proposed, which can reduce the error probability of quantum detector for discriminating DMCS. But there is an issue, a practical issue. There is a loophole in the implementation of using coherent states for CVQSS, that while transmitting the local oscillator, the system may be subject to a series of LOM attacks. Till now, researchers have already found several practical attacks against the transmitted LO, such as wavelength attack, LO calibration attack, LO fluctuation attack, clock synchronization jitter, and LO polarization attack. These LOM attacks have been investigated in point-to-point continuous variable quantum key distribution systems, and various countermeasures have been proposed. However, searches for multi-party CVQSS defending LOM attacks have barely been initiated, and since a practical CVQSS system is much more complicated than a CVQKD system due to increased number of users, it is reasonable to assume that the loophole of transmitting LO in CVQSS system is even more severe than that in the CVQKD case. So to solve this issue, a structure for CVQSS was proposed where both quantum and where both the quantum signal and LO are generated by the receiver. By applying this structure, LO does not need to be transmitted, thereby avoiding all LOM attacks. However, this solution has another problem, that while transmitting unmodulated quantum signal via an untrusted quantum channel, it may introduce new security vulnerabilities. Fortunately, there exists a local oscillator countermeasure for point-to-point QKD, which is immune to all LOM attacks. Although the introduction of reference signal may give rise to attacks against its intensity and phase, called reference phase attack, as of now these attacks have been prevented by real-time monitoring. Over the past few years, CVQKD using LLO has been theoretically and experimentally investigated, and the results have shown its feasibility in practical CVQKD system. A similar solution was introduced using LLO in CVQSS, and an initial demonstration was done. However, it appears to lack procedures for clear implementation in practice, and leaves the critical issue of phase compensation undiscussed. Therefore, there still exists a good enough system that can fill the loophole of transmitted LOs in CVQSS without introducing other troubles and address the challenge posed by LLOs. In this project, we extend the LLO technique from point quantum communication scenario to multi-party quantum communication scenario, and thus propose a practical CVQSS scheme based on local oscillator, aiming to thoroughly close the loophole that transmitted LOs of CVQSS system may be subjected to various attacks. First, we will present the design of LLO CVQSS system in which all LOs are no longer required to be transmitted via an untrusted channel. Then we will introduce a phase compensation method for multi-party quantum communication system to eliminate the phase noise caused by both fast and slow drifts. Finally, we construct a noise model for the proposed system and derive it security bound against both eavesdroppers and dishonest users. In this project, we focus on the 2-2 threshold for the scheme, but the general uh, solution method for the NN threshold can be further derived with similar ideas.
I am Aditya, and I am going to present the basic schematic of shown in the experiment, and also I will explain all the steps required to do this experiment. So, as you can see, the shown diagram is a basic 2,2 threshold of the LLO QSS. Uh, 2,2 basically means we have two user and one dealer, and this can be generalized when n, scheme also. So in the diagram, we basically have three different major blocks. One is the user one, another is the user, and third is the dealer. As we can easily point out, each of them have their own laser, uh, which is a unique point in this experiment. Coming to the user one state preparation. So user one generates a laser pulse, which is passed through a symmetric beam splitter, of which one pulse is delayed by half time interval and second pulse is passed through the amplitude modulator, phase modulator, and variable optical attenuator. And these two lasers are again recombined using a symmetric beam splitter, and we get the GMC state X1 plus IP1. And this pulse is basically sent to user 2. Now, in user 2, we have much more to do. So here also, there are we generate a laser pulse, which is passed through a symmetric beam splitter. Uh, and of the two pulses, one is passed through the modulators and the VOA, and another is delayed by half time interval. Uh, and the output of the user one is passed through highly asymmetric beam splitter, and we get so the two inputs of the highly asymmetric beam splitter is one is the user one input output, and second is the uh, modulated signal produced in the user two itself. Uh, as you can see here. So now we do two things here. One of the signal is used to measure the reference phase theta art, which is done here using the heterodyne detection. So we get one of the output of apps, and another input is the delayed signal of the laser of user pixel, and this is measured here. And second output of the apps is basically sent to the dealer. As you can see, the second output is basically represented as X1 plus IP1 plus X2 plus IP2 state. Now coming on to the dealer. So in the dealer part, we again have a laser which is called as the local oscillator, which is split by a symmetric beam splitter, of which one of the pulse is basically delayed by half time interval. and another the output of the user 2 is again passed on through the highly asymmetric beam splitter, and one of the output of the HAPS and the delayed signal is used to do reference phase measurement, known as the theta RD, and this is also calculated using is also measured using the heterodyne detection here, and the another output of the HAPS as well as the second output of the laser is again measured through the third heterodyne detector here, and which is basically the quadrature measurement XT comma PD. Now, so the next step in the experiment is to use the two reference phase measure, that is the theta R2 and theta RD, to get an updated data. So we basically correct the our quadrature outputs through the reference phase we get, and the updated data is basically represented as x2 prime, p2 prime, x3 prime, pd prime. And this is done multiple times to get sufficient amount of data. Yeah. Now, moving on to the next step. So next important step is the parameter estimation. So after a sufficient amount of data is collected, we basically divide our data into three parts. The first subset of the data is basically revealed publicly, and that is used for calculation of transmittance T1 and T2, uh, and the data is basically discarded. Uh, this calculation of T1 and T2 will be discussed by our other group member. Um, Moving on, the next step is basically, so this is a very important thing. So in this entire scheme, we basically consider that there can be one dishonest user, and we basically construct a method in which this dishonesty can be accommodated, and this doesn't affect the key. So what we basically do is we calculate secret key rates R1 and R2, where R1 is basically the rate calculated with the help of user one data, and R2 is calculated with the help of user two data. Now, uh, there is basically a protocol discussed in this paper, which will be discussed later, which basically show how we remove the user two data from the user one data to get just the information from user one, and how we remove the user one data from the combined output to get just the user two data, and each of these data are used to calculate the R1 and R2, the different rates, and final secure rate is taken as the minimum of R1 and R2. Now, so next important step is of course the key generation thing. So as I've stated, so as you can see in this diagram, the first subset of data is used for calculation of T1 and T2. In the second subset, we calculate R1 using by basically removing the user two data and just using like just calculating rate using the user one part. And the third subset is used to calculate the second rate using the by removing the user one part. Once we have the R1 and R, so using R1 we get K1, the key K1, and using R2 we have the key K2. And finally, the final key becomes K1 XOR K2. And the final encrypted message basically becomes M XOR K1 XOR K2. Now, the interesting one of the interesting thing of this result is that no single user can access the entire key, because as you can see, user one just have the access of key1, K key1, and the user two just have the access of key K2. So that's a thing, and hence we basically get a very secure and encrypted message.
So we now move on to the crucial phase compensation method that is essential to the working of the entire local oscillator setup for the continuous variable quantum secret sharing. Um, the importance of this is due to the fact that local oscillator was the um, reference measurement that we used for homodyne uh, detector to work, or heterodyne, and For local oscillator phase generations, the different users, including the dealer, will have to some sort of compensation mechanism for their reference phases that they use for their final measurements. So the original paper, as presented over here, points out two mechanisms for the phase difference. One being the delay that is characteristic to the creation of the reference signal, that is detailed in the previous section in these coils. And another is the so-called fast drift, which is due to the initial phase difference in the reference phases of each of the user and the dealer. So to individually compensate for each of these, first we look at the fast drift, which is easier to understand in the sense that it requires a simple counter rotation, which is done by the measured phase differences due to the setups used over here. In the original setup, the heterodyne detectors help us to measure phase differences, which then allow us to determine the relevant counter rotation that will help us uh, bring it bring the axes in an aligned position so that the secret sharing can be done in a reliable manner. So the calculation shown over here, the diagram and the expressions are simplistic and self-explanatory. The detector, the dealer's X and P, which is obtained by heterodyne measurement, uh, is a combination of the ones that they receive from the users, and the expression for that is their rotated rotated X and P for the users plus some noise. The rotation is done by the relevant phase drift, which, as we just discussed, occur due to this fast and slow mechanism. Fast being due to the phase difference in the initial phase reference, and slow being due to the delays that are not directly measurable, which we will counter using a different method. So there are two steps of phase compensation, as can be seen over here. After that, they have listed the calculations. So as is evident, the compensation in the actual data points, as in the X and P, has to be done due to the initial assumed phase reference phases that the users and the dealer are using. So the phase drift is characterized as just the difference between the initial reference phase of user 1 and that of the dealer, and phi 2 is just the difference between the reference phase of user 2 and that of the dealer. After that, they have taken into account that the measured reference phases using the heterodyne detectors for dealer and user 2, since user 2 lies in a sort of railed connection, so they'll also get some signal from user 1. The reference signals they receive also have some factor of delay um included in them by virtue of experiment design. Um, Also, then writing the phi 1 and phi 2 in terms of those is a simple rearrangement exercise. We just substitute 4 and 5 into 2 and 3 to get these equations. And then finally, we know how much to rotate the measured phases, measured x2 and p2 for user 2 to obtain their phase corrected for the fast drift, phase corrected for the fast drift data points. Similarly, uh, the dealer does a rotation and they get their data points corrected for fast drift as well. Their noise gets rotated as well. The additional noise term over here is covered in later sections. It's a Gaussian noise. So finally, as they note here, by doing this rotation, the initial phases of both user 2 and dealer's lasers can be deemed to be identical with that of user 1's laser, the initial phases, which is illustrated by figure 3b, where they have compensated for the fast drift. Now, the issue is that simple measurement by heterodyne detectors is not enough to isolate the delays, as um, they will talk about, and they say that their method to estimate the delay is by releasing some of the sets of data that the users and the dealer will be sharing in order to get an estimate for their correlations. And by using the correlations, since they'll have a significant since they'll have a distinct component, rather a distinct component of the delay factored in inside of them, the delay term can be isolated by using the correlations. User 1 and user 2 both theoretically know how much in what functional form the delay should be related in their x points and p points to the dealer's x point. So they can use the data that the dealer gives about their x point through whatever channel in order to estimate the phased delay written as theta delay d1 and theta delay d2 over here, and finally just divide those sines and cosines in order to get isolate the delay phase. And finally, then they do a counter rotation on their data, and that helps the axes of measurement, that is the reference axes that we had been trying to align all along for reliable secret sharing. They have been completely aligned with the dealer's axes. The procedure anyway requires the sharing of a lot of data points in order to estimate the transmittance and the um, key rates in order to know their reliability and to be able to see whether this whole scheme of secret sharing is going down successfully. So some of those data points can be shared, and the advantage, as they later describe, is that eventually all of the total phase drift is compensated. The good thing is that in each step, not all of the users are disclosing their data at once. So it's secure through and through. Uh, to compensate for the fast drift, user 2 the and the dealer are not sharing any information. They are just compensating using the heterodyne detection for the reference phase that they got, and for the slow drift correction, only the user 1 and user 2 are correcting their phase drifts, and the data of the dealer is the only one that's shared. User 1 and user 2 don't share any data in this step. So neither of the steps reveal the data of all of the parties. So these steps are secure, and overall they have achieved using locally generated local oscillators, that is reference phases for measurement that are locally generated and still manage to carry out continuous variable quantum secret sharing. That was the key aspect that made the entire scheme work. Since local oscillators were prone to attacks from outside, they developed a method that would allow the local oscillator compromise to be circumvented by keeping the local oscillator reference phase generation at each of the user and dealer junctures, and any of the sort of miscommunication that could happen, not exactly miscommunication, but uh, off the measurements that could turn out to be off, they compensated for it using uh, estimates and a clever sharing of phase differences and delays one by one, not all parties sharing at once. So that was phase compensation, which was essential for the functioning of LLOCV QSS.
Hi, I am Vedant and I'll be doing the methods for calculation part. The correlation between user 1's x quadrature and dealer's x prime quadrature is given by this expression. Here, since x1 p1 and x2 p2 and xn prime are independent of each other, the terms x1 p1 x2 x1 x2 x1 p2 and x1 xn prime equals to 0. So the final expression comes out to be this, a single equation. Similarly, the correlation between user 1's p quadrature and xt prime is given by this expression, where p1 p2 is equal to x1 x2. Next, the correlation for user 2 with respect to xt prime is given by this expression, and correlation of for user 2's p prime with respect to xd prime is given by this expression, where p2 p2 is equal to x2 x2. Now we come to the calculation of the lower bound of the secret key rate r1. So r is given by beta iud minus chi de, where beta is the reconciliation efficiency, iud is the Shannon mutual information between user 1 and the dealer, and chi d is the maximum information available to eavesdroppers and user 2 on dealer's measurement. This is when we calculate r1. When we calculate r2, the the user 1 turns to user 2 and user 2 changes to user 1. So we combine the excess noise, and the channel added noise referred to the channel input is given by this, where epsilon is the total excess noise, and the noise added by dealer's heterodyne detector is defined by this, 2 minus eta plus 2 VEL upon eta, where eta is the detector efficiency and V electron is the electronic noise, and the overall noise is given by chi line plus chi heterodyne by T1, where T is the transmittance. And the Shannon mutual information is calculated by IUD, which is equal to log 2 V plus total noise, overall noise, upon 1 plus total noise, where V is equal to 1 plus VU1, where VU1 is the modulation variance, and chi de, which was used directly in the calculation of r, is calculated using this expression, with the summation expression, where g is given by x plus 1 log to the base 2 of x plus 1 minus x log to the base 2 of x, and lambda 1 2 are the eigenvalues of g, where the eigenvalues are given by this expression a and b, where a itself is a long expression and b is another expression, and lambda 3 and 4 are also the eigenvalues of G, where C is also another expression, D is also another expression, and lambda 5 equal to 1.
Hi everyone. In this video, we'll be covering the final three sections of the paper: the noise model, the discussion, and the conclusion. These sections answer the practical question: once we've built this system, how well does it actually perform and what limits it? Let's get into it. So, the paper builds a complete noise model by identifying every physical source of imperfection in the system. The total excess noise is written as epsilon equals epsilon am plus epsilon le plus epsilon adc plus the epsilon of phase and the rest of the error, which is written in equation 23 in the paper. Each term is a concrete physical origin. The epsilon am comes from the amplitude modulator's finite dynamic range, which means coherent states aren't prepared perfectly. The epsilon Le corresponds to the photon leakage. The reference pulse isn't perfectly isolated from the quantum channel, so some of its photons contaminate the signal. The epsilon ADC comes from the dealer's analog to digital converter, which has finite number of quantization bits. The epsilon phase is phase noise, which we'll look into at detail next. An epsilon rest captures everything else. Standard imperfections would see any CVQKD systems. What's important here is that the paper doesn't just treat noise as a black box parameter. Every term is derived from hardware specs, things like extinction ratio, ADC bit depth, and detector efficiency, using the global parameters listed in the table in the paper. So, phase noise. Phase noise is the dominant and most interesting noise source. So it gets its own slide. There are two components. Fast drift. Phase fast drift is caused by the jitter between free-running lasers at different locations. In a standard system, this would be a serious problem. But here's a key insight specific to LLO CVQSS. Because each user's quantum signal and reference signal are generated by the same laser, the drift term epsilon drift is exactly zero. That's a direct benefit of the LLO architecture. What remains is epsilon error, the phase measurement error from heterodyne detection of the reference pulse. This scales as VU divided by mod of alpha r's times t, mod of alpha square times t. As the channel transmittance t drops with distance, this term grows. That's the irreducible floor of the phase fast drift. Phase slow drift is different. It comes from the transmission delay along the optical path and clock synchronization errors. Unlike fast drift, this can't be measured directly. Instead, the paper estimates it from the statistical correlation between user data and disclosed dealer data. The residual error is captured by the parameter V slow, and critically, it can be improved simply by disclosing more data in the estimation step. Now here's the central tuning problem of the LLO design. The amplitude of the reference signal mod of alpha square appears in both epsilon Le and epsilon error, but in opposite directions. If you increase epsilon a mod of alpha square, your reference pulse is stronger. So you estimate the phase more accurately and epsilon error goes down. But a stronger reference pulse also leaks more photons into the quantum channel. So epsilon E goes up. As you decrease it, the leakage drops, but your phase estimate gets noisier. At short distances, T is large, so the phase estimation is naturally good, even with a weak reference. So you want small mod of alpha R square. At long distances, T is tiny, and you need a strong reference to get any useful phase information. So you want larger alpha mod R square. So here is the figure. The optimum at each distance is exactly the crossover point where epsilon error equals epsilon Le. The paper shows this in figure 5, which is listed here, and the author continuously optimizes alpha R mod square at each distance rather than fixing it globally, which gives meaningfully better performance than any fixed pattern. Okay, so the figure 4 here plots secret key rate against transmission distance for 4 scenarios, and this is where the noise model pays off. The best case, ideal detectors and perfect phase slow drift compensation reaches about 80 km. This tells you the ceiling of what the system can achieve when phase compensation works perfectly. The irreducible limit here is epsilon error, which can't be fully eliminated because channel loss and reference channel noise always exist. The second curve, still ideal detectors, but with a V slow of 0.001, drops to about 65 kilometers. This tells you how sensitive the system is. Imperfect slow drift estimation. The gap between these two curves is entirely recoverable by disclosing more data. So moving to practical detectors with efficiency 0.6 and electrical noise 0.01, the max distance drops further to around 55 kilometers. That's because weaker detectors reduce the SNR of the reference pulse measurement, raising epsilon error. And the worst case, the practical detectors plus imperfect slow drift compensation gives about 45 kilometers. The inset of figure 4 makes a clean point. In every case, maximum transmission distance is hit precisely when total excess noise epsilon equals the tolerable noise threshold, epsilon tolerable. The noise model and the performance curve are completely consistent. Figure 6 looks at how the choice of modulation variants affects performance. And this is something unique to multi-user CVQSS versus standard two-party CVQKD. In standard CVQKD, only Alice modulates. Here, every user has to modulate their own Gaussian coherent state, so both VU1 and VU2 matter. The key findings from figure 6 are: first, smaller modulation variances are generally better. The best secret key rate at 5 km is achieved with VU1 roughly below 15 and VU2 below 25. As distance increases, these optimal windows narrow further. Second, this is physically intuitive. The system is more sensitive to VU1 than VU2. That's because the final key rate R is taken as the minimum over all CVQKD links. Since user 1 is the farthest from the dealer, the link between user 1 and the dealer sets the bottleneck. So V1 has more leverage over the final rate. One caveat the paper is honest about in practice. You don't know which link will be the minimum. So you have to estimate it from the real rate. So the theoretical bottleneck and the practical one may differ. Figure 7 asks, does it matter where user 2 sits along the fiber? The answer is yes, significantly. The x-axis is the ratio L1 over L, where L1 is the distance from user 1 to user 2 and L is the total distance from user 1 to the dealer. So when this ratio is small, user 2 is close to user 1. When it's close to 1, user 2 is close to the dealer. The result is clear. The secret key rate decreases monotonically as the ratio increases across all total distances tested, 55, 80, and 100 kilometers. The reason ties back directly to the noise model, where user 2 is close to the dealer, the transmittance T2 is large, and looking at the noise equations, every excess noise term, epsilon AM, epsilon LA, epsilon ADC, epsilon error, has a T2 over T1 scaling factor. So a large T2 amplifies all noise contributions simultaneously. The practical recommendation is clear. Users should be clustered as close to user 1's end as possible, not spread evenly or pushed towards the dealer. Finally, figure 8 generalizes to n users, which is what we actually need for a real quantum network. The paper tests two configurations. In the symmetric case, all n users are evenly spaced. In the asymmetric case, all users are clustered close to user 1 within 1% of the total load. Two results stand out. First, performance drops as you add more users in both cases. This is expected. The security proof requires treating n-1 users as potentially dishonest, and each additional dishonest user contributes more to the Olivo information problem. Second, this is the headline result. Asymmetric placement supports up to 30 users, while symmetric placement maxes out at 25. The maximum transmission distance in the two-user case reaches 112 km. Importantly, even at 30 users, the asymmetric scheme stays above the PLOP bound, the fundamental repeated limit for meaningful distances. That's what puts this in the realm of practical viability rather than just a theoretical result. To summarize what this paper contributes, first it closes the local oscillator loophole by generating local oscillator locally at the delay rather than transmitting it through untrusted channels. The system is natively immune to wavelength attacks, calibration attacks, LO fluctuation attacks, clock jitter attacks, and polarization attacks, all in one architecture. Second, It provides a complete and practical phase compensation method. The two-step approach, correcting fast drift via reference phases, then slow drift via correlation estimation, is fully specified and each party only needs to revise their own data locally without revealing extra information. Third, it gives a rigorous noise model that maps physical hardware parameters to a security bound valid against both external eavesdroppers and dishonest users within the group. And fourth, numerical results are strong. 30 simulation users 112 km maximum distance and performance that stays above the PLOP bound. The paper closes with two directions for future work. The author plans to investigate quantum machine learning as a tool to further improve key data distance and finite size analysis, going beyond the asymptotic regime to account for real block sizes. Remains open. It's also worth noting the honest limitation that n threshold analysis for n greater than 2 is extrapolated rather than fully derived. And reference pulse attacks on intensity and phase still require real-time monitoring. Though existing CVQKD techniques handle this, overall LLO CQVSS is a meaningful step towards practical multi-party quantum communication. It takes a theoretically sound protocol and makes it robust against the class of attacks that could most threaten a real deployment.
Hello, I'm Kshitish Bhattacharya, and now we will be looking into the IPython implementation part of our project, mainly the data processing that is being done. So let's begin. So this implementation is implementation of the data processing part. So because we have a local oscillator in this case, so which is with the dealer himself to prevent any compromise on the local oscillator signal. This results in some different kind of processing that is to be done in terms of the states that are received by the dealer and sent by the user. So this is what is being implemented in the paper in this code. So which has four parts. First is the phase compensation method. This arises because there is some phase delay that the coherent states gain or while they are being transmitted, which we need to account for. Second is the estimation of the transmission coefficients between the users and the dealer. The third part is to find out if the communication itself has been compromised with presence of an eavesdropper. So we find out the mutual information available between the dealer and the users and the maximum information available to the eavesdropper, which uh, which we use to find out the key rate, finding a secure key rate from which we could use further the error correction algorithms and establish the keys. So we begin with first importing the libraries. Now these parameters we have set up for the entire pipeline, some of which are being given in the paper, which are mentioned as from reference, which you have directly taken from. Some of which we ourselves have put up, and these can be changed to understand how, under different circumstances, this entire pipeline works, and how the noise changes and mutual information differs. So we move with it. So this is the generating data. So we'll be generating coherent states. So this is the plot which shows the x1 and p1 of each coherent state. So these are mean is zero and zero centered Gaussian distributions. Now the paper has recommended to have same variance across the x and p quadrature, like a circle. Here we have tried to implement in terms of rotated ellipse, where the distribution of the states is like an ellipse, which is rotated. This is done to show that this model also works in such complicated systems. Uh, yeah, so that is the reason to generate rotated states. One important thing is that the x1 and x2 have they should not be correlated, which is an important part for the model to work, and we'll see why. If we need to extract correct coefficients, we need them to be not correlated to each other. So we are first checking the covariance to make sure that it is close to zero, so we can proceed. Now we will begin with adding noise to the data. So when the data coherent states are communicated, there is of course a noise in terms of the phase delay. Uh, So there are two types of noise, fast noise and slow noise. So the fast noise is different for each coherent states. There is some phase shift which we are taking it in terms of a Gaussian noise, and there's a slow noise which the phase shift is applied to the entire data that is being passed through. So it depends on the channel characteristics, and for the faulty channel, some faults in the channel would add noise. The second one is the reference that is added to the user 2's data. So the reference signal of user 2 differs from that of user 1. And so there is to be a natural phase difference between the data generated by user 1 and user 2. So what user 1 calls as 0 is not what user 2 will call as 0 in terms of phase. So post noise and rotation, we will see the data. We see that the user 2 data shows signs of rotation, right? So now we go to the detector. So the detector will get a combined data from both the users, and plus there will be some noise. So this equation here explains the data that is being received by users. This eta is the detector efficiency, and T1 and T2 are the transmittance of each channel. Here we show the data received by the detector. Now, even the detector would have a different phase as compared to the user 1 and user 2, which itself is computed by heterodyne detectors. So we can move on to the setup. So we can see that this is the reference signal of user 1, and it is different from the reference that the user 2 or user 3 are using their lasers. So this is computed from the heterodyne detectors present uh, in with user 2 and the dealer. So we are using the same theta that we did to shift things. Now we rotate the data to get x3 prime and x2 prime. Now the communicated coherent states are divided into three parts. So first part is used to find out the transmittances. Second part is used to find out the key rate, and the third part is used to get the key. So for that, we'll split the data. Which will like 20% of the data will be used to calculate the transmittance, and 10% for the keys. So this is just taking the required data. Now this data will be used to calculate the theta delay, the phase delay that has occurred due to the noise we have added. And these are the formulas which again were given in the paper. Right now, it is important to understand why we need the covariance to be zero, because if the covariance is not zero, then the P2 and XT contains both x1 and x2 terms. Now, because the covariance between x1 and the user 1 and user 2 is zero, the contribution of user 1 in this data gets cancelled out while we are taking this average over there in a product. Uh, this is sign for an average. So that is why we need the covariance between the user 1 and user 2 to be zero. Now, after post processing, this is the data, and we could see that the user 2 has been rotated back to its reference base. So we get x2 prime, x1 prime, and x2 double prime, as mentioned in the paper that are now we calculate the channel transmittance. This is by simply inverting the formula by which the dealer gets the data. So again, covariance being zero is important because the x1's we have to only consider x1's contribution and x2's contribution will be zero. And you could see that the actual and estimated T1 values are close. Same with T2. Now we'll compute the channel noise. The noise that is due to different uh, processes that take place. So this also in the paper they have shown steps. So the first is due to the amplitude modulation. Then, as we were converting digital data into analog, there will be some noise, and there will be a phase noise that we are adding to the phase delay. So it's the total noise, which is the summing of things. So all these values have been taken from the reference for the simulation. Now we calculate the key rate, which corresponds to the formula of mutual information minus information available to the Eve. For this, again, we'll extract some subset of data from which we'll calculate R, which is not going to use for the key calculation. So here we have the function to call the maximum information that Eve has, which is chi D. This is again taken from the paper and which uses this G function. Now, if in case in case any user is being dishonest, to prevent breakdown of the communication, we remove the user's contribution by subtracting the contributions in itself. And this, after we remove user's contribution, and then we calculate the key rate for the first user, which will be 0.3. Now we repeat the same process, but for user 2. Here we subtract user 1's contribution and we can see the ellipse the shape. Note that here we are not seeing the original ellipse because the declarer got a rotated ellipse when the user 2's data was sent. So we get that shape only, but you can see that it is quite different from the data that the dealer itself has seen. So you can see that there is a sharper ellipse. And this is the key rate for user 2. And the R is the minimum of both of those errors, which we can see the bottom. Okay. So this was for a very ideal scenario. We'll understand what happens in case of change of parameters. So we know that transmittance is quite high. If we reduce the transmittance, we'll understand that the data that is being reached to the dealer is very low. It's very noisy, and this would affect the key rate, which is a negative, which means that the communication has been completely compromised. The presence of E will affect the transmittance or add some significant noise, which is areas R1 turns out to be negative. This is also the case if we increase the noise when we have higher transmittance. So we check this is not negative. So again, the channel is compromised. However, this noise with 0.0 and 0.05 is slightly higher, but would still give positive results. But you could see that this has been reduced by a factor. Previously, this was a much higher number. Now we'll try with the circular data as recommended by the paper. So yes, V1 and V2 are 4. So we just take this to LS. You can see this is more circular data. The transmittances are close to the actual one. After removing each user's contribution. So we can see R1 is 0.12, R2 is 0.4, this is the positive. So this is the working of our code. Thank you.